Hi, it's Justin Zeltzer here for the first of 6 videos into statistical inference. This one's to do with likelihood, sufficiency, and nuisance parameters, which are the sort of foundational concepts of statistical inference. And laid out in front of us is the path we're going to be taking on this video. I'm going to start with an example, and I tend to do that because I like exploring the intuition behind the concepts we're learning, rather than just bowl you over with theoretical formulae to start with. So this first example will be a discrete distribution, a binomial one at that. And after we have a quick look at that and develop the intuition behind statistical inference, we'll have a look at the theoretical concept of likelihood, which will include discussions of likelihood ratios. We'll have a look at the likelihood function and, of course, the log likelihood function. Now, as you'll find, we love logging things in the likelihood game. We'll then discuss the topic of sufficient statistics, or statistical sufficiency. And here we'll develop ways of reducing the amount of information we need in order to conduct inference on our parameter values. After that, we'll have a look at another example, and here it'll be a normal distribution, so a continuous distribution, and we'll see that these concepts of likelihood still apply in a continuous setting. From there, we go to look at multiple parameters and how likelihood can apply to estimation of numerous parameters at the one time. Unsurprisingly here, the 2 parameters we'll be looking at as an example will be the mean and standard deviation, and relating that to our normal distribution that we just had an example of. And finally, we'll look at nuisance parameters. So that's when you have multiple parameters and maybe one of those parameters, say the mean, is of primary interest. And if that's the case, the other parameters like the standard deviation might be considered nuisances. And we'll see how to get rid of those from our likelihood functions. So without further ado, let's get into example 1. So here we're looking at the prevalence of thalassemia in Greece, which is a blood condition, but not a fatal one in its minor form. Just means you have slightly less than robust red blood cells in your body. So straight up, let's consider 2 possible population prevalence values for this blood condition in Greece. The first suggestion might be that theta, which is our population parameter for the prevalence, is 7%, 0.07. Or it could also be 0.08. Now, on the left side here, if the true population prevalence was 7%, and let's say we took a sample of size 100, so both of these plots here are for samples of size 100, you would expect maybe 7 out of those 100 people to have thalassemia. This here represents the probability distribution of all the possible outcomes out of 100 people. And 7 indeed is the highest peak, so that's the most likely outcome. But you could also get 6 people having thalassemia out of 100, and that's quite likely as well. The probability diminishes though as we go down to 5, 4, 3, and 2, etc. If you look on the right, you'll notice it's a slightly different distribution. Of course, this is where theta is 8%. So again, understandably, the probability is the highest for an outcome of 8 out of 100 people in our sample with thalassemia. 7 is also quite probable, and then it ducks down quite swiftly after that. Okay, so with that under our belt, let's presume that we do indeed have a sample of 100 Greek people, and 6 out of those 100 people tested positive for thalassemia. Now again, this is where I'm trying to develop your intuition behind what's going on here, but if I was to ask you which theta above is more likely given this sample outcome, I'm pretty sure you're going to tell me that the left one is more likely. It's more likely that theta is 7% than it is 8%. And your intuition would be correct, but in this topic we're going to find ways of quantifying how much more likely one is than the other. But before we can quantify that difference, we actually need to make a key flip in logic. And this is what you need to get your head around right now. You'll notice that we have a fixed sample outcome here where there's 6 people out of 100 testing positive for thalassemia. To assess our likelihood, we're actually going back to this distribution, which is dependent on a fixed parameter value. So what we do is we say, if theta was 7%, what is the probability of getting an outcome of 6? And that probability is 0.153. That's the height of that bar right there. So hopefully you can see what I mean by a flip in logic. In reality, we know there was only one outcome, 6 out of 100. But to generate what's called a likelihood, we have to go back to these probability distributions around our fixed theta. And then here we go again, for where theta is 8%, the probability of getting 6 out of 100 is 0.123. So these two numbers then become our likelihoods. Even though they were probabilities on our distributions above, we can now call them likelihoods. So just going over this notation, this has the likelihood of theta being 0.07 given y is 6, given we have an outcome of 6 out of 100, is equal to 0.153 and 0.123 for theta being 0.08. And at this point you might rightfully ask, well, wouldn't we want a function that provides for a fixed sample outcome a distribution of likelihoods for our population parameter, theta? Well, that's indeed what a likelihood function is. We use the term likelihood now because we're talking about this population parameter, theta. And it's here where that logical flip is now complete. We have our two likelihoods that we generated before for theta being 0.07 and theta being 0.08. I'm sure you could imagine that for having 6 out of 100 in our sample with thalassemia, a more likely value of theta would be 0.06. And you can see that's actually at the peak of this distribution. So it's with this that we've now completed our flip from probability density functions for our sample outcome to what's called a likelihood function for our population parameter value. So hopefully you've developed a little bit of intuition now behind what's coming up. Now let's deal with the theory of likelihood. So the official definition would be that it describes the extent to which the sample provides support for any particular parameter value. Higher support corresponds to a higher value of the likelihood. So for a discrete distribution, this is how we read these. This is how we read the formula here. This is the likelihood of a particular value of theta given a sample outcome y. It's actually equal to the probability of y given that particular population parameter value. And this is exactly that flip in logic that we saw in the earlier example. The likelihood of a particular theta for a given y is equal to the probability of a particular y for a given value of theta. That's the flip. And more generally, we use this f subscript y to mean the probability density function of y, or the PDF, which applies to both discrete and continuous distributions. So for a continuous distribution, it's exactly the same thing. So for a continuous distribution, we can just relate to this final term here, which is the probability density function. But a point to note about the likelihood, and we'll find this out as we go, but the exact value of the likelihood is completely meaningless by itself. It's only informative when we look at the relative value comparing two potential values of theta. And in doing so, we can construct this thing called a likelihood ratio. So we can look at the likelihood of one particular value of theta and compare that in a ratio to another particular value of theta. And that provides us with something that's useful, but the individual likelihoods themselves don't mean anything. So let's take it back to our example just to ram it home. The likelihood of theta being 0.7 for our thalassemia example was 0.152. And the likelihood of theta being 0.08 is 0.123. Now, we can construct the likelihood ratio by just dividing both of those, and we get 1.124. And that tells us that a population prevalence of 7% has 1.124 times the support of a population prevalence of 8%, given our sample. So let's now look at the likelihood function. Again, the official definition: for a given sample, you can create likelihoods for all possible values of theta, and this is called a likelihood function. So notice here we no longer have subscripts for our theta. This is a likelihood function where you provide a value of theta and get output a likelihood for that potential parameter value. In a sample of size n, the likelihood function takes the form of a product, which might not be so clear as to how this works when we're using a binomial distribution. But if you think about the formula for the binomial PDF, it's actually a product of individual binary outcomes. But hold that thought, because we're going to have a look at how it works on the next slide. And even further along, we'll see how this formula really comes into its own for continuous functions. Let's just appreciate that we can construct a log likelihood function as well, which is given this sort of curly L. And if you're taking the log of a product, you can rewrite that as the sum of individually logged terms, which is just simple log laws. Now let's apply this to our particular example. So, find the likelihood function of theta given n is 100 and y is 6. So 6 people out of 100 had thalassemia. Well, here we go. This is that exact binomial PDF. And let's take a moment just to have a look at it. We would have quoted this. If you've had a look at binomial distributions before, you might have recalled this just from memory. But having a look at it now, hopefully you can see that it indeed is a product of individual outcomes. So if you have 100 samples, if you had 100 observations, and there were 6 people with thalassemia and 94 people without thalassemia, look at what happens. You're multiplying 6 lots of the population parameter to 94 lots of 1 minus that population parameter. So here's that product, and that's our likelihood. This combination function is just a feature of the binomial distribution because it doesn't matter what order our 6 thalassemians line up in. So the likelihood ratio, if we were to try to find that for 2 particular values of theta, theta 0 and theta 1, we can ignore the actual beginning. We can ignore the NCY component because it's going to be the same on top and bottom. So it's only this sort of functional part after the 100C6, which we need to put into this ratio. Now to find the log likelihood function, well, we're just going to take the log of this function up here. So it's the log of NCY plus the log of theta to the power of y, and that y is going to come out the front. Hopefully you're familiar enough with your log laws. So we've got 6 log theta and 94 log 1 minus theta. And what we can do when we find the log likelihood of particular values of theta is we can compare them by subtracting them. So again, I've tried to put theta 0 and theta 1 into this little turquoise bubble here. But if you put in theta 1, you can do 6 log theta 0 plus 94 log 1 minus theta 0. So that's 1 log likelihood. And you can subtract another log likelihood. And the difference between the two is a relevant metric, which we can use, which we'll be using later on. So it's important to note that for these likelihood functions and log likelihood functions, the theta is the variable. So I've just added a final little point here about the log likelihood, is that you can construct this in a way that says that this first bit is almost like junk material. We don't really need to worry about it. It's all it has is something to do with y, which is the sample outcome 6. It does not depend on theta at all. So the active component of this log likelihood is this second bit that has theta in it. We can almost ignore that first component completely from our analysis. Okay. So with that done, let's have a look at sufficient statistics. Now here, a statistic, let's just label it TY, is any quantity that can be calculated purely from a sample. So it's independent of the population parameter. And we say it's sufficient if it conveys all the available information about that parameter theta. So here's an example. To estimate the average height of students watching this video, let's presume I sample 100 viewers of the video. And here's my sample set. I've got 174 centimeters, 181, etc. Let's say I have 100 people in this sample space. Now the statistic of the sum of x, the sum of all these heights, is 17,183, let's just say. Now if I want to estimate the average height of students, let's call that theta, all I really need is the sum of these 100 viewers, right? As soon as I have that sum, I can calculate a sample mean. I divide that by 100. I actually don't need the full sample at all. You could hide that from me and I'd still get all the information I need to estimate the average population height. So we'll come up against this a few times, but when your likelihood can be decomposed into some component that only has reference to y and another component that relates to theta through some kind of statistic, then that statistic is sufficient. And we'll see a concrete example of statistical sufficiency coming up now in example 2. Now for example 2, we're looking at systolic blood pressure in pregnancy. So let's say here I've got a sample of 5 pregnant women that have their systolic blood pressure taken. And it's considered to be normally distributed with a population standard deviation of 10. Now let's use the tools we've been given and see if we can apply them to a normal distribution here to extract a likelihood function. So as we said, the likelihood function is the product of individual probability density functions. And in this case, the normal probability density function looks a bit like this. It's a bit gross. You've got pi there, you've got the 2 parameters mu and sigma squared, and you have your value of y as well. In this case, because we've set sigma to be 10, I'm going to replace all of the sigmas in this formula with 10. So it's going to be 2 times pi times 10 squared, which is 100. And here it's going to be 2 times sigma squared, which is again going to be 2 times 100. So in this case, the PDF for each of these individual observations will look a bit like this. In other words, for a given value of mu, for a given mean, the probability density for each of these potential outcomes can be achieved by just chucking these values in for y in this formula. Okay, so if we're going to have a product of 5 of these, think about it, we're going to have 5 lots of this first term here, 1 on the square root of 200 pi. And I can take then that out the front. Then we'll have the rest of the equation here. And because we're multiplying 5 exponential functions, we can raise into the power of this exponential function a sum of all these values. It's just a simple index rule, right? So this is now the product of 5 individual observations, the PDFs of 5 observations. And if you take a look closely, you'll notice this first bit out the front is just a constant term. It's got nothing to do with anything really. Doesn't have anything to do with the sample or the potential population parameter mu. And if I expand the brackets here, again, it's going to, if you want to follow this line by line, you can. All I'm doing here is expanding this brackets on the top of this summation. So it's going to be y squared minus 2 lots of y times mu, and then plus mu squared. And don't forget there's a summation in front of each of those. So what I've done here is I've split it into a component that only has something to do with the sample here, and a component that has something to do with mu. And when we have that component that's got something to do with mu, check out what form y is in. You've got the sum of yi. And guess what? The sum of y is therefore a sufficient statistic in this instance, because that's all we need to know to generate the active part of the likelihood for mu. as the rest of the equation could be considered a constant for a given sample result. And there we have it. If I want to replace the sum of y with our statistic t, a more general statistic t. So basically what that means is I don't need to know these individual 5 values here. All I need to know is that the sum of it is whatever it is, and I could find a usable likelihood function for mu. And here's that equation again. You can see we've done exactly that. We've separated it into a part of the likelihood that relates only to y, which is the fixed part, and then the other part which relates to theta, but through some kind of statistic involving y. Although here, just note, we haven't used theta, we've used the more specific parameter, in this case, mu. So let's check in with Jupiter over here, our big friend multiple parameters. You'll notice in the example we just provided that I had given you the population standard deviation being 10. I've sort of set that in stone. But if we let that be loose, our likelihood function becomes a little bit more complicated. Now, a normal distribution is perfectly defined by 2 parameters, mu and sigma, the mean and standard deviation. So in this case, our likelihood function indeed contains both of these parameters, mu and sigma, both being the variables in determining this likelihood function. So the question you might ask is it possible to generate sufficient statistics when there are 2 variables at play? So we saw that we had the sum of our observations became a sufficient statistic to create a likelihood function for the mean. But when there's a likelihood function with 2 variables, what sort of statistic can you get that would be sufficient for this? Well, bear with me here. Let's try to again open up this quadratic and take the denominator here, the 2 sigma squared out the front. So here we have 2 different statistics, T2 and T1. Now, if I define something called Ty, which indeed has 2 separate statistics, the first being the sum of all the observations, and the second being the sum of all the observations squared, well, this indeed is how we could write our new likelihood. T2 here is the sum of y squared, and that's exactly what you're going to get for the first term of this expanded quadratic up here. So even though we call this a sufficient statistic, this is a vector where it has 2 individual statistics attached to it, T1 and T2. So of course we're going to need a little bit more information if there are 2 parameters at play here, mu and sigma squared. But still we can find a sufficient statistic requiring, in this case, only the sum of y and the sum of y squared to provide us this likelihood function. So we don't need all of the observations. All we need is the sum of y and the sum of y squared. Now this example is pretty cool. Let's have a look at this. Again, it's the systolic blood pressure example, and here are the 5 observations from pregnant women, their blood pressures. If you consider that the sum of all those values is 590 and the sum of all those values squared is 70,000 odd, here is an expression for the likelihood function where you could sub in those values for the sum of y squared and the sum of y. And when you sub in those values, you can get a pretty cool distribution. I've got this up on an Excel spreadsheet. Somehow I managed to do this in Excel, and I'll attach it to the video in the notes below it, or in the very least, it'll be on the zedstatistics.com website. But what this likelihood function now can provide us is a 3-dimensional net of the likelihoods of all the combinations of mu and sigma. So you can see here that mu is likely to be somewhere around the 116, 118, 120 mark. And it's not that easy to see, but sigma might be somewhere around that 12, 13 mark. That probably represents the highest ridge on this plot here. But don't get too wowed by the colors here. I'm not sure that's the greatest way of presenting this. It's a bit distracting, but they're just representing different levels that you can kind of appreciate the height from a 3-dimensional space on. But essentially the concept I'm trying to get through here is that the likelihood function we met in the first example was a two-dimensional curve across one parameter, mu. But when you've got two parameters, mu and sigma squared, of course we're going to need another dimension. So it's a three-dimensional likelihood function. It doesn't need to stop there. You can have 3, 4, or 5, or k parameters that you're estimating. Of course, you won't be able to draw it geometrically, but it in theory at least would have 3, 4, 5, or 6 dimensions. Now you might be looking a little bit ahead here, and you might be thinking that peak at the top is probably a pretty important point. And you're right. It's actually called the maximum likelihood estimate. And if there's numerous parameters, say there's 3, 4, or even 5 parameters, it might take quite a decent amount of computer power to try to find that peak. In this case, it should be quite simple because there's only 2 parameters. But you can imagine a scenario where with more parameters being estimated, that peak becomes quite arduous, even for a computer program to estimate. And that leads us quite neatly into discussions of nuisance parameters, which is our final little topic in this video. So let's say that one of these parameters is of prime interest, and in this case, well, it's most likely going to be the mean in these cases. And the standard deviation here would be considered to be a nuisance parameter. So here's that likelihood function again. What we can do is we can replace nuisance parameters in the likelihood functions with their estimates. And in doing so, we create this thing called a profile likelihood. So what's an estimate for sigma squared? Well, the estimate, of course, is your sample variance. So if we have our sample, we can find our sample's variance, which we can term s squared. And in replacing sigma in the above equation with s, it becomes a likelihood function just for the parameter mu, which we can call the profile likelihood. And what does that look like? Well, there's our sample again. If we wanted to create our sample standard deviation, we could use that formula that we're quite used to, and it's 12.63. And we could sub that into this function. You could sub that actual value 12.63 into the function here for s. What that's essentially doing is it's taking our three-dimensional net here, our likelihood function across 2 parameters, and creating a two-dimensional likelihood function, much like we saw right at the beginning, a cross-section, if you will, at our sigma value of 12.63. So we can find that peak value of mu for a given value of sigma being 12.63. And this is called a profile likelihood function. So that's it for the first video into statistical inference. Again, all the other videos will be up on zedstatistics.com or on the YouTube channel zedstatistics.